Welcome to the explainer. Deep beneath the surface of our oceans, there's this colossal engine running. It's basically a planetary circulatory system, and it dictates our weather, shapes our coastlines, and really makes life as we know it possible. Today, we are diving deep into its powerful heart, the Gulf Stream, and the continent-spanning conveyor belt it drives, which is known as the AMOC. All right, just a quick heads up before we really get going. This is a more technical look into the physics and the dynamics of this whole system. We're going to be building on concepts we've already touched on, so if this topic is totally new to you, you might want to check out our first, more foundational explainer on it. So here's our roadmap for today. We're going to start with something you've probably heard of, the powerful Gulf Stream, before we zoom out to see the massive global system it's a part of. Then we'll get into the nitty-gritty physics that drive it, understand its huge role as a climate regulator, and finally, we'll have to confront the evidence that this critical engine might be in trouble. Okay, let's kick things off with the part of the system most people know, the mighty Gulf Stream. People call it a river within the ocean, and honestly, that's a perfect description. Its power and influence are just immense. For centuries, we knew something was out there in the Atlantic. Sailors could feel its pull. But it was actually Benjamin Franklin who first put a name to it. He was trying to figure out how to speed up the mail. Since then, our understanding has just been a story of accelerating technology. We went from a submarine drifting for 30 days back in '69 to satellites that now give us this complete, real-time picture of this incredible oceanic river. But here's the thing. As huge as the Gulf Stream is, it isn't the whole story, not even close. It's actually just the most famous piece of a much larger, planet-spanning engine, the Great Ocean Conveyor. Okay, this slide really gets to the heart of it. Think of the Gulf Stream as a fast-moving highway on the ocean's surface, mostly pushed along by the wind. The AMOC, that's the Atlantic Meridional Overturning Circulation, well, that's the entire global transport system. It's this slow, deep, massive conveyor belt that's driven by water density, and it connects all of the world's oceans. Now, the engine's scientific name sounds complicated, but it actually reveals its own secret. Thermohaline circulation. Thermo for heat, and haline for salt. It all boils down to one simple but incredibly powerful concept. Cold, salty water is denser, it's heavier than warm, fresh water, and that single principle is what drives this entire global system. So this process really kicks into high gear up in the North Atlantic in what some call the Greenland pump. So warm water from the tropics shows up, it releases its heat into the cold air, and it gets colder. At the same time, evaporation is pulling fresh water out, leaving the salt behind, so it gets saltier. This cold, salty, and now very dense water just sinks thousands of meters to the ocean floor. It creates this powerful downdraft that literally pulls the entire current along behind it. This right here is the heart of the AMOC engine. All right, so let's pop the hood. What are the specific physical forces that govern this huge flow of water? Let's get a little technical and really look at the complex dynamics that make this whole system tick. It's really just a beautiful dance of physics. First, you've got wind. The trade winds and westerlies are literally pushing the ocean's surface. But the water doesn't just move in a straight line. Because our planet is spinning, the Coriolis effect bends the current to the right. This deflection piles water up against the continents, creating something called western intensification, which is why the current is so fast and deep there. And finally, a principle called conservation of potential vorticity kind of acts like a governor on the engine, making sure the flows stay stable and narrow as it shoots north. And this quote from NASA Goddard just nails it. That Coriolis effect we just mentioned, it's not just some abstract term. It is the force that physically squeezes this huge movement of water up against the coast, concentrating it into that powerful, focused jet that we call the Gulf Stream. I mean, the numbers here are they're almost impossible to wrap your head around. At its peak, the Gulf Stream moves 150 million cubic meters of water every single second. Scientists have a name for this unit, a sverdrup. And to give you some perspective, 150 of them is more than 100 times the flow of every single river on Earth combined. That is just a staggering amount of power. So we have all this physical power, but what does it actually do? Well, it turns out this ocean engine doesn't just move water, it moves heat. And by doing that, it fundamentally shapes our entire global climate. And this is arguably its most critical job for life on Earth. The AMOC acts like a massive heat conveyor. It is single-handedly responsible for moving about a full 25% of the total heat from the tropics up toward the poles. It's like a planetary scale radiator, making sure our world doesn't have a scorching equator and frozen poles. This heat pump effect is precisely why northwestern Europe has such a mild, temperate climate. I mean, take a city like Bergen in Norway. It's at the same latitude as southern Greenland, but its port stays ice-free all winter long. Without that warmth being delivered by the AMOC, its climate would be brutally cold, much more like Siberia. And it's not just about the big picture climate stuff. Its influence pops up in countless other ways. Its warm water can act like high-octane fuel for hurricanes. It's a biodiversity highway for marine life, carrying fish and larvae way up north. Where it crashes into the cold Labrador Current, it creates some of the thickest fog on the planet. And its sheer power can even affect sea levels and coastal erosion along the U.S. East Coast. And that brings us to the most critical part of this entire story. This powerful, ancient, unbelievably complex system is starting to show signs of instability, and it's raising some very serious concerns that it could be approaching a tipping point. To really understand the threat, we have to ask this one simple but honestly pretty terrifying question. What happens if this engine, which has been running for thousands of years, just stops? Well, the biggest threat is a huge influx of cold, fresh water coming from melting ice sheets, especially Greenland. This fresh water pours into the North Atlantic and it dilutes the salty surface water, which makes it lighter, less dense. And if that water isn't dense enough to sink, that Greenland pump gets weaker and the entire conveyor belt slows down, or potentially shuts down altogether. Now here's the crazy paradoxical part. A collapse wouldn't mean uniform warming everywhere. For Europe, it would actually trigger a regional deep freeze. Cities like London, which are famous for their mild winters, could see their average temperatures just plummet, plunging the whole region into dramatically colder, harsher conditions. And the consequences would be catastrophic, and they'd be global. Beyond Europe getting colder, the U.S. East Coast would see significant sea level rise as the current weakens, and water literally piles up against the coast. It would disrupt vital monsoon rains in South Asia and Africa, which would threaten the food supply for billions of people. It could even reduce the ocean's ability to absorb CO2, creating this dangerous feedback loop that actually accelerates overall global warming. And this is not some distant, theoretical problem. The data we have now shows the AMOC is already at its weakest point in over 1,600 years. And while the exact timing is still up for debate, some models are warning that a collapse isn't a matter of centuries away. It could happen within decades. Okay, so let's just quickly recap the 5 essential takeaways from all this. 1. The GulfStream is just one part of the much bigger density-driven AMOC. 2. The AMOC is a huge conveyor belt powered by that sinking water near Greenland. 3. This system acts as a massive heat pump for the planet. 4. Melting ice threatens to shut this pump down by diluting the salt water. And 5. If it does, the consequences would be severe and global, from deep freezes to rising seas. And that leaves us with one final and pretty heavy thought. This planetary engine has been a source of incredible climate stability for thousands of years. The question we really have to confront now is whether our own actions are pushing this ancient, vital system past a point of no return.